Okay, new chapter 4.1. We'll call this video A. This chapter is exponential and logarithmic functions. You've all done exponents, you've all done logarithms, so that part of it shouldn't be too terrible. But we're going to start out with inverse functions and exponential functions and all that stuff before we get into logarithmic notation and logarithmic functions. So this first one is called inverse functions. And if you remember an inverse basically undoes something. So, when we have a function, it undoes the function. So we'll get into what that means here in a minute. But what happens is, well, let's look at the relation h equals the set -8, 5, 4, -2, -7, 1, 3, 8. Okay, we have that set of coordinates right there. So, let's look and see what happens if we invert these. So, if we take the inverse of h, we get 5, -8, -2, 4, etc., etc., until we're done. So that's the inverse of those. And one of the things that you'll notice is when you graph these, if we have our graph like this, and we have a graph of all of these points, and then we graph these points, they're going to reflect across the y equals x-axis. That axis, it's a 45-degree angle that goes through the origin. So if I have a point here, it's going to reflect a point there. If I have one here, it's going to reflect here, or here, it's going to reflect there. So it will always reflect across the x equals y axis whenever we do an inverse. Alright, so let's look at the inverse relation. Interchanging the first and second coordinates of each ordered pair in a relation produces the inverse relation. So basically, just like I had right here. So we take this, and we take that relation and turn each coordinate around from here to here and here to here. We get what is called an inverse relation. Okay, so let's get rid of all that. Alright, so an inverse relation. If a relation is defined by an equation, interchanging the variables produces an equation of the inverse relation. Meaning, if we take a relation and we define it by an equation. So let's define this relation by an equation. Okay? And we want to find the inverse. We just switch our letters around. Like that. This is the inverse of that. So if we were to graph each of those, we would get something like that. So here is our original, right here. And here is our inverse. See, it flips across this y equals x-axis. And the way you graph that is you just did your x and y for this equation, and your x and y for this one, and graph, and you get what you've got. Okay, so you can see that this is a function because it will pass the vertical line test. Alright, so let's look at inverses and one-to-one functions. Okay, so left-hand side of the page is the pictures on the bottom of page 349. And notice what's going on here. As we put in an input, it kicks out an output. So an input, output. Each one of these only goes to one output. Even though 02 and 04 go to the same one, 202 only goes to 37. 204 only goes to 37. It doesn't go to another number as well. Alright, let's look at the right-hand one. Each one of these, only one number goes to one number. Okay, over here we have 96 and 98, both go to 32. That isn't the case here. All of these numbers only go to one number there. Okay? So let's look at the inverse. Let's look and see what happens when we look at this postage thing and we inverse it. We turn it around. Basically, our inverse is going back. Alright, so the inverse of the postage function is not a function because, see, when we go back, 32 goes to two numbers, 29 goes to two numbers. Now notice what happens over here with this one. It doesn't matter if we go the other way. Each one of these numbers only goes to one of these numbers. So notice, let me move this out. Notice that both this and this are functions. This one here is a function, but our inverse, when it goes back, is not a function, because each one of these has two outputs. Because what happens on the inverse is the output now becomes the input, and this becomes the output. So it goes and then okay, so input to output, input to output. So input to output can only go from one number to one number to be a function. And what happens here? One number to two numbers. So therefore, the inverse is not a function. Now, if we were to have an equation with an x cubed in it, one of the things that's nice about an x cubed is it always works. In the cubing function, each output corresponds to exactly one input, so its inverse is also a function. So we don't run into one being a function and its inverse not being a function when you have a cubing function. So when it does that, when you go like this one here, one number to one number and then one number back to one number to where they both work, we have what is called a 1-to-1 function. Okay, important to know. This is actually the letter 2, or TO, 1-to-1 function. But that's what happens when they both work both ways. Alright, so the way you write an inverse, if it is a function, the way you write it is like this. This is not an exponent. Okay, it just means the F inverse. Okay, so if the inverse of a function is also a function, then we can say this right there, F inverse, because the F represents a function. Alright, so a one-to-one function. Kind of told you a little bit ago what a one-to-one function, if it works this way and is a function, and it goes back this way and it's a function, it's going to be one-to-one. Now the book does some more mathematical jargon. Ooh, you know that word. A function f, on the bottom of page 350, is one-to-one if different inputs have different outputs. So if A does not equal B, then f of A, the y value, does not equal the function of B. So if A does not equal B, well, here's an A, here's a B. Okay, we're going to plug numbers in for the A and B. If they're not equal, then these two also cannot be equal. So if that gives me a 3 when I put 1 in the function machine, and this gives me a 6, these are not equal either. Okay? If they were equal, then we'd have both 2 and 1 pointing to the same number. So what would happen if these were equal? I'd have 1 and 2, and then I'd have a 3, because both of these would be equal, so that means my functions would be equal, which means that points there and that points there, which is fine. But 3 then, if I looked at the inverse, would point to both of those numbers, and once your input points to two numbers, it ceases being a one-to-one function. So that's why it says f of A cannot equal f of B. So this number cannot be equal, these numbers cannot be equal, because then you go here to here, and then here to here. Okay, and then it works as a one-to-one function. The second part of that says, or a function is one-to-one if when the outputs are the same. So, oops, I'm sorry, the outputs, that's the input. Alright, let's put an output right here. if the outputs are the same, the inputs are the same. Okay? So if A equals B, that means both of these numbers here have to be the same. And then this number has to be the same. So that's pointing like that. But look what happens. Alright, so that's a function. And remember what I said? If we point back, look what it does. It points to that number. It points to two different numbers. But since it points back to the same numbers, it really is going 3 is to 3. And then this one points back to the 3. Okay, so it is a 1-to-1 because these two numbers are the same numbers. So when it points back to both of them, it's actually pointing back to the same number. So it does work. Alright. So top of page 351, properties of 1-to-1 functions and inverses. Alright, if a function is 1-to-1, then its inverse is a function. So basically what we'd said before. If this points to here, so that's a function, and then I say its inverse is a function, then it's 1-to-1. Alright? Alright, so let's go to example 3 here. The rest of that information there on top of page 351, we're not going to worry about all of that. It gets really complicated talking about domains and range. Alright, given the function f described by, okay, so here's my function f, 2x minus 3. Prove that f is 1-to-1, or prove that it has an inverse that is a function. Okay? So here's what we do. We look at the bottom of page 350, and so what we're going to do is we're proving that that's true. Alright, so if it's 1-to-1, that means that my function of A must be equal to my function of B. And it also means A has to be equal to B if that's the case. Alright, so let's go ahead and look at this. Let's look at the function of A using this. Function of A is going to be 2A minus 3. Function of B is going to be 2b minus 3, because all we did was replace our x with an a and a b. Okay, according to what we have up here, these two functions are going to be equal. 2a minus 3 equals 2b minus 3. Okay, let's go ahead and solve. Okay, cancel that. We get a equals b, which is what we have up there. So if we said, okay, if these two have to be equal and these two have to be equal, well, let's take the function of both of these, set them equal to each other, and see if we get these. And we do. So therefore, it is a 1-to-1 function because of the bottom of page 350. It follows the principle for a 1-to-1 function. Now, we also could have used the top. A is not equal to B, but I like working with the equals better. So anyway, I'm going to stop this one, and we'll start on example 4 in the next video.